logistics of the quiz, and there's a couple of things I'd like to say right here. One of them is that you will be allocated seating. Okay, so you'll be assigned a seat number. So check that out. It's going to be posted on Canvas. You click your seating chart and you get a number. Find your name. Find the number. There's also a map of this lecture hall, so you can just walk to your seat, just like that. Second thing is that you can bring your calculator. You should bring your calculator, okay? Bring your calculator. Bring your pen or pencil and eraser. Those are the things that are allowed on the exam, plus the index card, okay? People have questions about that. Yes, we can have an index card, 3x5, folks, 3x5. You can write anything on it, front and back, and you can bring it with. You can have one index card, not 20, just one, okay? And you can use it as something that, kind of a mental support system, so to speak, because most of the information that you need is already on the exam. Formulas that you need are actually given. You don't have to figure things out, really. So hopefully it's a self-sufficient exam, but I can understand that such a note card is a good friend to have, all right? So you can bring that. We'll be starting exactly at 10. So, typically the lecture starts about 1.5 minutes late, okay? That means 1.5 minutes past 10, but that's not how it's going to work on Friday, okay? So we're going to do it on time. We're going to start at 10 sharp. People who come late just have less time to complete it. So be on time, okay? So you may want to run a little quicker out of the previous class. Yes? Yeah, that's going to be posted tonight, right? So the keys will be posted tonight for the practice quizzes. Any other questions? Yes?
If your assigned seat is like a right-handed seat, do you need a left-handed seat? Or will you be able to switch seats?
Yes. So if you're left-handed, this row here is left-handed, and you're assigned a right-handed seat, you can just jump over to the end of the row. Fortunately, there's like only a few left-handed people typically, so there will be enough spaces for them to sit. In practice, my experience actually is that it actually doesn't really matter which seat you sit, because sometimes you can just go like this, and it's gonna, you can shield yourself from your neighbor, which is kind of nice when you're left-handed. So, up to you. You can move to the left-handed seat or not. Anything else? Okay, pretty good, pretty good. Make sure you attend the discussion sections this week. If you have any questions, that's a good place to bring them up. Practice the practice quizzes, also the worksheet for this week, so you are well prepared. Yes? Yeah, you first.
Okay, if our discussion is on Friday the same day as the exam, do you recommend doing that one or turn earlier one?
Well, it's up to you. It's maybe kind of nice to go to the morning session, because then you get a great refresher of all the things that are relevant, so you walk in well prepared. But it's up to you, I would say. Yes?
Will today's materials be up in
No, because today is lecture 10, and the quiz covers 1 to 9. So, I hate to say it, but it's not. Today's beautiful material will not be on the quiz, unfortunately. Okay. So I'll just start lecture 10, which is a great lecture. And this will not be on the quiz, but this will be, of course, on a subsequent quiz. All right? So this is important. It's also important because we are inching closer to our goal, which is, of course, describing the electron in the atom. And we have done a lot of finger stretching exercises to get to that point. We've seen electrons swirling around in certain spaces, one-dimensional potentials, a ring, a harmonic potential. Okay, so, and we have found wave functions for those cases. We've found energies for those cases. We found something about probabilities, where the electron can be and where it cannot be. Okay, But we haven't really hit the nail on the head, and that's why we want to move to something that looks more like this, okay? This is a sphere. Okay, so today we're going to talk about an electron that moves on a sphere. Does that fully describe the electron in the atom? Not really, but it's a lot closer. The sphere is basically just the surface of a sphere, okay? Not the inside of a sphere. So we're not moving from the origin away, back and forth. We're only moving on a sphere of a fixed size. Let's say you can normalize it so the size is 1. So that's what we're going to look at. Basically, we're going to look at a two-dimensional wave function that is confined to a sphere. All right? That sounds weird, but it's not really weird. Think about an ocean wave. That is a two-dimensional wave. You've seen the wave in a two-dimensional square box. That is a wave, 2 dimensions. But now we're going to have that wave, and we're just going to slap it onto a spherical surface. We just require that the wave has amplitude only on that surface. So this is the geometry of the surface, but if we assign a wave function to it, then it looks something like this. Okay? What does it mean? Well, you see red and blue. Let's say blue is negative, red is positive. Right? So the wave function here, psi, has values that can be negative or positive. And it looks like a wave. You see it like it goes negative and it comes up, it becomes positive, and everywhere there's a white thing, there is 0 value. So it basically goes from positive to negative. This looks like a wave. It looks like a wave that is confined to a two-dimensional surface that happens to be a sphere. Right? So this, again, is a two-dimensional wave on a sphere, and that is a great place to start describing our electron in the atom, because something like this must happen in the atom as well. If we add now the radial coordinate to it, then we have a good description of the atom. Okay? Here we have the surface, the spherical surface, that is best described by 2 angles, theta and phi, the polar and azimuthal angle, that basically describe the entire sphere. So what I'm going to do is I'm going to do that. I'm going to describe this sphere and try to solve the Schrödinger equation for the wave function on this sphere. Okay, a couple of approximations, or not really approximations, but facts. The first one is that R equals a constant. That means this is truly a sphere. R is constant. Okay, so I don't have to worry about R. I do have to worry about this angle theta, because that's going to change, and the angle phi. You see that? Theta and phi now define where the point of that arrow will land on this surface. So the point on this surface is fully defined by the values theta and phi. That's why theta and phi are my relevant coordinates. And you know that this, of course, is the situation for spherical coordinates. Okay? You've seen this hopefully before. Position in x, if you want to relate it to Cartesian coordinates, there's a relation between Cartesian coordinates and spherical coordinates, and if you want to write it in x, then you have to use this expression here. R times sine theta times cosine phi. For y, we have this relation, R times sine theta times sine phi, and z is R times cosine theta. So this is a way for us to relate the Cartesian coordinates to spherical coordinates. We're going to leave the Cartesian coordinates behind, and we're going to focus on the spherical coordinates. Why? Because I want my Hamiltonian to be expressed in the angles theta and phi, not in x, y, and z. Because x, y, and z has 3 coordinates, while theta and phi is only 2. So 2 is a simpler problem than 3. That's what I want. Okay? And here is the result. Again, we're not going to fiddle with the derivation of this whole thing, because that is already done many, many years ago by other people, and we can just learn from their achievements and take note of the results. So, what is the result? remember, I have here the Hamiltonian, and we have seen it now many times, and my goal is to describe it in 3 dimensions, but now describe a sphere in 3 dimensions using the theta and phi angles. This is the result of that kind of exercise for the case when the potential energy is 0 everywhere on this sphere. So V equals 0, as we have done many times now. V equals 0. So there's no potential barrier on this surface. It's all 0. There's only kinetic energy. This is the result. I see that my Hamiltonian looks like something familiar. H bar squared divided by 2m with the negative sign. Then a funny symbol, it's a triangle upside down with the square. That is the del squared, the del squared. If you didn't grow up in this country, then it's called nabla squared. All right? So what is that thing, the del squared? The del squared is basically the second order derivative with respect to space for these coordinates, for the spherical coordinates. So it looks like this. The prefactor stays the same, but this del squared is between parentheses. You can see it has something that depends on r, a second order derivative with respect to r. That r derivative is going to be not important because r is a constant. So when r is a constant, then its second order derivative is going to be 0. So I can cross that one out for this problem because we're not concerned with the radial coordinate, only the spherical surface. The second term is 1 over r squared with another funny symbol that is a capital lambda with the square, and that thing looks like this. Again, this looks pretty ugly, but don't worry about it. You don't have to memorize it, okay? We're just going to use it to come to a final result, okay? So don't be scared by the way it looks, because you will see in the end we'll get something that is hopefully a little bit more manageable. This lambda squared contains the second order derivatives along theta and phi, okay? It's part of this expression. You can see, indeed, it only has dependencies on theta and phi in it. No r dependence. So this thing is what I have to focus on. Right? I see here a second order derivative with respect to phi, and here's one for theta and another one for theta. So in the end, it's also a second order derivative with respect to theta. So this is what I have. This is what I have. This thing has a name. It's called Legendrian. So in case you see that written somewhere in the textbook, then you know what it is. Basically, the Legendrian is the second order derivative with respect to theta and phi in spherical coordinates. That's what it is. It has the same information as the previous Hamiltonian, but I'm just rewriting it and considering it in the theta and phi coordinates. Everything else is the same. So what I want to do, of course, is to solve this time-independent Schrödinger equation. I know what it looks like, and I'm having wave functions, or I would like to have a wave function that only depends on those two coordinates, theta and phi. Okay, so psi as a function of theta and phi is plugged into the Schrödinger equation, and my job is to solve this eigenvalue equation for this particular case using this Legendrian. Okay, so this is what I'm having. This is what I have to solve. This is what I have to solve. The other terms are 0, and this is what I'm left with. There's a prefactor, again, h bar squared 2m, but look, there's also an r squared now. You may recall that m times r squared is capital I, which is the moment of inertia for angular motion, right? M times r squared is capital I. Then I see this Legendrian operator that operates on my wave function, that then generates a constant, E, which is the energy, times the wave function again. This is the math that I have to solve. Okay, what do? Something quite similar to before. I'm going to take this prefactor and divide it out on the right-hand side so that I get on the left-hand side, on the left-hand side I divide it out, and on the right-hand side I get another prefactor. I also write mr squared as I. So what I get is 2I times E divided by h bar squared with the negative sign. Now I have on the left-hand side a clean expression, which is basically just the operator, the Legendre, operating on the wave function. We'll be generating this constant times the wave function. So, the good thing is for us that there is a beautiful solution to this problem. The math is very dense, but the results are somewhat manageable, as you will see. Because the eigenfunctions of this eigenvalue equation are the so-called spherical harmonics. It's a series of functions, it's well known in mathematics, and they have very beautiful properties because they basically describe the wave on a sphere. Okay? The wave function, I don't call it psi anymore, give it a slightly different name. I'm going to call it y. But y is basically psi. Okay? Same thing. Y has two quantum numbers, L and ML. Why two? Well, one way to think about it is that I have two dimensions. I have two dimensions. The sphere is a two-dimensional thing, and therefore I am expecting two quantum numbers that quantize these states. And of course, it's a function of theta and phi. This function can be written as a product of two things. Two functions, one of them only depends on phi, the second only depends on theta. That's kind of cool, right? So, this function, this is the capital theta function, only depends on the parameter or the variable theta, the little theta, and this capital phi only depends on the variable phi. We also see that this last function here, the thing that only depends on phi, has one quantum number, ml, whereas the function that depends on theta has two quantum numbers, L and ml. Okay, so that is the structure of the solution. Now, what do these functions now look like? I mean, they have certain shapes, so let's look at that. The shapes, of course, change as a function of what L and ML are. And these L and ML you are probably familiar with. Okay, because these are the quantum numbers that define the periodic table, all right? L is an integer and it runs from 0 to infinity. And ML is also an integer, but it is not independent of what L is. ML has certain values depending on whatever L is. So it seems that ML runs from L to negative L in integer steps. Okay, that's given here. So whenever L is 2, ML is negative 2, negative 1, 0, 1, 2. 5 possible values for ML whenever L equals 2. The L is sometimes referred to as the quantum number for orbital angular momentum, and the ML as the magnetic quantum number. Okay, so L relates to the quantum number of orbital angular momentum, and ML to the magnetic quantum number. We'll see why they have those names as we move on. So here's a list of the first 3, or actually 4, functions of y. The first functions of the spherical harmonics, starting from the lowest possible quantum numbers. It turns out that this function that only depends on phi, that last function, is exactly the same as the solutions of the particle on the ring. That's what we did last time. It's basically a complex exponential that depends on ml times phi. So that's kind of nice. Same thing, because it has the same kind of symmetry, circular symmetry, so it's actually part of the solution. The lowest possible spherical harmonic has L equals 0 and ML equals 0 and is simply a constant. What kind of wave is that? That is a wave that is simply constant all across the sphere. It's kind of a boring wave. The second one is when L equals 1 and ML is 0. In that case, the function looks like some constant times cosine theta. So it's just a cosine theta that is slapped onto a sphere. Then, if L equals 1, there can also be values of ML that are either plus or negative 1. And in that case, it looks like this. Sine theta times now something that depends on phi. Because ML is no longer 0, that means it has also a phi dependence, which is this complex exponent. Right? So the complex exponent is present in this solution, but not in these two, because here ML equals 0. So it doesn't depend on phi. There's of course many more. We could go on, and the higher the quantum numbers, the more complex these functions become. Okay? And so that basically means, think about this, the simplest wave is just a constant on the sphere. The next simplest one is basically a cosine. That means half of the sphere is positive, half of the sphere is negative. All right? Still pretty simple. Then I'm going to add things to it. So at some point I'm getting lots of hills and valleys on the sphere. It gets more and more complex. Here it is. Simplest one, L equals 0, ML must also equal 0 in that case. Constant on the sphere. Then, L is 1. There's 3 solutions in this case. Namely, ML can be negative 1, 0, or 1. So there's three solutions. All of these solutions are individual solutions of the Schrödinger equation. And they are forming a complete set. That means all of these solutions are so-called mutually orthogonal. Okay? You can see that this is basically, this is a cosine or a sine on a sphere. Okay? Whenever you see the green color, it's kind of 0, and then positive and negative. Yes?
So all 3 of the solutions for L equals 1 are all mutually orthogonal?
Yes, correct. Correct. Yes. L equals 1 doesn't mean that these 3 wave functions are the same thing some way, somehow. They are individual solutions because each spherical harmonic has a unique combination of quantum numbers. L has a certain number, ML has a certain number. If L equals 1, then ML can have different values. So when it's 1, it's not the same than when it's negative 1. Those are 2 independent solutions. So here, so far, we have seen 4 independent solutions to this problem. They are mutually orthogonal. That means they are completely independent of one another. L equals 2 has, of course, 5 values of ML, therefore 5 independent solutions. ML is going to run now from negative 2 to positive 2, so that labels the different quantum numbers for these particular spherical harmonics. You can see that it's a little bit more complex now. Look, for instance, this is the best representation here. You can see now it goes through more zeros, okay? So there's additional so-called nodal planes on the sphere. How about this? It gets more and more complex. L equals 3. Now I have 7 possible solutions of ML. That means 7 independent solutions. And you can see that the shapes of this wave becomes more contorted, more kind of like bulgy. Okay, more curvature, if you wish. That also means higher kinetic energy. The more curvature the wave function has, the higher its kinetic energy. So I can say something about the energies of these states. The lowest one must be the top. Then L equals 1, all of them have the kind of the same symmetry, aka the same kind of basic shape. It's just like the orientation that changes. So they're independent, but they have the same energy because they have the same curvature, and therefore these are degenerate. So all the states with L equals 1 are degenerate states. They have the same energy. All states with L equals 2 also have the same energy because they have overall the same kind of curvature. the same kind of kinetic energy, and so forth. The same for L equals 3. The more complex these shapes become, the higher the kinetic energy of the function must be. But in one row, they are all the same energy. L equals 4, and so forth. Look at that. Isn't that pretty? I told you it's going to be a good lecture. You didn't believe me. Look how pretty that is. Pure mathematics. But this looks already like, let's be honest, orbitals, right? Looks like orbitals. It's not complete, because we only consider the surface. We also need to consider the radial coordinate. So we don't get this lobiness in there, just get the surface effect. But it's already there, folks. It's already there. We're getting very close. Okay, now, I told you that these functions y are mutually orthogonal, meaning if I take two functions and I multiply them and integrate over space, I must get 0 if these functions don't have the same quantum numbers, or 1 if they do. Yes?
So all of these are mutually orthogonal, or only like the ones within the same?
All of them are mutually orthogonal because all of them have unique quantum numbers, and all solutions to the Schrödinger equation are mutually orthogonal. Each unique solution is orthogonal to another unique solution. It doesn't matter if they have the same energies, or they happen to have the same quantum number L. As long as ML is different, they are different solutions. Does that make sense? The only thing that is similar between these functions that are all independent in this last row is that they happen to have the same energy. They have the same energy, therefore they are degenerate, but they're independent solutions. Just like you and I can have the same age. Okay? I'm actually a little bit older than you, but let's imagine that I have the same age as you, and that means we have two people the same age, but we're still independent. All right? I mean, it doesn't matter if we have the same age. We're still independent individuals. Same here with all these L equals 4 states. This function and this function, the overlap integral, is 0 if they don't have the same quantum numbers. Meaning, delta ML, ML prime, that means that ML must be the same for both, and L must be the same for both. If either one of them is not the same, then the whole integral is going to be 0. That is the definition of orthonormality. Therefore, they are mutually orthogonal. Okay? Now, this integration here is the integration over the sphere. It looks like this. Okay? It has a sine theta in it, d theta d phi. This is the so-called Jacobian for the two-dimensional integration on the sphere with constant r. That's just how it is. So again, it looks a little scary, but that's just how it is. So if you do an integration of this kind, never forget to put the sine theta there because it's part of it. It's part of the volume of the surface element. The surface element is this element right here. Theta runs from 0 to pi, and phi runs from 0 to 2 pi. That spans the entire sphere. If you let them run over those limits, you basically describe every point on the sphere. So I'm integrating over all possible locations, then I can prove that these functions are mutually orthogonal. Another way of writing that is, of course, to use our new notation, which is the bracket notation, that you haven't quite loved yet, but you will. And I can write it as follows. This is the ket, L, ML. That is what matters here. What are the quantum numbers? That defines the state. And on this side, L prime, ML prime, that is another function from the same set. I make this bracket thing, so the bracket, and this whole thing just represents this entire expression, which is way shorter, and if you learn how to read this, it contains the same information. It basically checks the condition of orthogonality between the two states. The answer is the same, because it's the same expression. Yes?
Where's the sine theta in that?
We don't need it, because this integration simply means that I integrate over all relevant space. I don't care what it looks like. As long as they are mutually orthogonal, I don't need to know anything about the actual shape of the wave functions. I know that they are mutually orthogonal, and that is what this thing states. Our goal is to make things simpler. We don't have to go through the motions of completely solving these integrals, which is a lot of work, can be painful, okay? But we want to make use of some intrinsic symmetries and properties that these integrals have. This is the property that the integrals have. This is all we need to know at this point. We just need to know that they are mutually orthogonal. They are orthonormal. That is what this statement says. So we don't care how you carry out the integration, what the volume element is on the sphere. We don't care. I know these two functions are part of the same set, and therefore they are mutually orthogonal, and that's it. Okay, so those are the functions. What about their eigenvalues? What are the eigenvalues of the spherical harmonic functions? So here's the same kind of eigenvalue equation that we solved, or that people solved for us. We just looked at the solutions. And we see that the eigenvalues of the spherical harmonics have the following value, namely negative L times L plus 1 between parentheses. Those are the eigenvalues. Okay? Those are the eigenvalues of the spherical harmonics. Now remember, when we started deriving this equation, we actually said that the constant in front of the wave function was this, 2ie divided by h bar squared. That's the constant that we had sit there. Now we have a solution, which is that, and therefore those two numbers must be the same. So the eigenvalues of the spherical harmonics are those on the right-hand side. The energy was part of that prefactor, so we just have to rewrite this thing in terms of E. And so I can do that as this. This is what I'm getting. E, the energy of any given spherical harmonic, equals L times L plus 1 times this constant h bar squared over 2i. That's it. And it actually kind of complies with what we just talked about, because the energies of these spherical harmonics only depend on L and not on ML. We saw that. This whole row, they were degenerate because they all have the same ML. They have the same energy. They're mutually orthogonal, they are independent, but they are degenerate, and therefore their energies do not depend on ML, only on L. Let's look at those energies for a second and compare them to what we know about angular momentum in a classical sense. Several lectures ago, we said that classically, the angular momentum is the moment of inertia times the angular frequency, I times omega. That is how big the angular momentum is. Now, how big is the angular momentum here? Okay? So, in classical terms, if I know the magnitude of angular momentum, that is going to be L squared divided by 2i. L squared divided by 2i. That's what the energy is. And from that I can see, beautifully, that this L squared represents the square of the magnitude of angular momentum. I'm going to use that and relate that to what I just did quantum mechanically up above here. Because I have now two expressions for energy. This is generally true, this is classical, and the one up there is the quantum mechanical solution. Okay? So this is the quantum mechanical solution we just derived here. This is the classical expression, and I'm going to equate that. I can see this 2i happens to be in both, so that's going to cross out. Okay? And that means that I can write this. L squared equals L times L plus 1 times h bar squared. Take the square root of that, and I get this. The magnitude of angular momentum is this. It only depends on L. That's why L is called the orbital angular momentum quantum number, because it quantizes the angular momentum that a particle can have, that the electron can have when it occupies that state. What is the magnitude of an electron that occupies a state, a spherical harmonic state, that happens to have a certain L? Well, if L is 2, plug 2 in here, do this calculation, and you know what L, which means the magnitude of angular momentum, is. Right? What about this other operator that we looked at last time? LZ. LZ. LZ is the angular momentum of a particle that has ring-like motion. Remember that? If you have ring-like motion, then the angular momentum points up or down, depending on the direction of the angular motion on the ring. So what happens if I operate with this operator LZ onto my new solutions for the two-dimensional wave functions on the sphere? So let's do that. Okay, you can see here, that's what I do. LZ times this wave function is LZ, this is the wave function right there. Okay, it has the two parts, the theta function and the phi function. And if I write out, last time I remember, this LZ depends only on phi. So I only operate on the phi part of the spherical harmonic. That means this last function here, that guy. This LZ only operates on this last function, not on this theta function, which depends on theta. This LZ doesn't have theta in it, it only has a phi in it. It's the first order derivative with respect to phi. That's what we saw last time. And so when you do that, and remember, the function phi is exactly the same as the solution for the particle on the ring, okay? And therefore, the value that it generates when it operates on it is the same as before. And last time we found ml times h bar. Okay? So what is the difference between the magnitude of angular momentum and this value, ml times h bar? Well, it's the following. This is a so-called projection of the angular momentum along one of the axes. Well, the magnitude is the actual magnitude of the orbital angular momentum of the electron. So if I have a sphere and this particle is swirling around, I can determine its angular momentum, magnitude, how big it is, but I can also make a projection on one of the axes. Okay? So what is the angular momentum when I project it along z? That is the value. It's ml times h bar. It's just a vector. If I have a vector like this that points in this direction, I can determine its length. Okay, that's the angular momentum, or its projection onto this axis right here, on the z-axis. Okay, so whenever something is pointing in one direction or in a particular direction, I can determine the magnitude and its projections on the axes. So this is the magnitude of the projection onto the z-axis. It depends on ml. You see that? It doesn't depend on L. So the projections onto the individual axes actually depends on ml. Whereas the magnitude of this vector depends on L. Okay, this is just another way of writing it. We have done it before. LZ is operating on my spherical harmonic that I can simply write as this. I don't need to know anything else. When it operates on it, it simply generates ml times h bar. I know what ml is because ml is given in this ket. It has a certain value. It generates ml times h bar. Every time LZ operates on a spherical harmonic, it generates an eigenvalue ml times h bar. Finally, let's look at a molecule and see if we can use this spherical harmonic framework to also explain the orientation of a molecule, the molecular motion, the rotational motion of a molecule. Let's say this is a diatomic molecule. This thing can spin around, can spin around in 3 dimensions in all kinds of ways, right? So this is a 3-dimensional problem. It can spin around, but basically in spinning it kind of like traces a surface, if you wish. So I can actually formulate this problem in the same way as I just did for the electron on the sphere. What I have to do though is to kind of use again this concept of a reduced mass. Okay? Because I have 2 particles here, I'm going to write it in terms of the reduced mass, and then the reduced mass effectively traces spherical motion on the sphere, because those fully define the allowed spherical motion, rotational motions of this molecule. What are the solutions? Exactly the same. Okay? This mu is now the reduced mass times r, okay, which is the distance between the particles, is basically my I. That's 2I. Okay? So this is again 2I, h bar, the same. This j is called j, but it was previously called little l. Same thing, because it's the same problem. It's the same problem. So what does it mean? If you have a molecule that is allowed to rotate, it basically says that the energy that this rotational motion can have is quantized. Okay? Interesting, but true. Because you can see that the energy values here are quantized, because J is basically little l, and little l runs from 0 to infinity in integer steps. So, that means, strangely enough, if I have a molecule, and I ask myself what kind of rotational motions is it allowed to make, not everything. Because only certain energies are allowed. It's because the molecule is small. If the reduced mass is going to be very, very high, then this whole thing is going to go to 0 and it loses its meaning. But if it's very light, then its rotational motion is quantized. Only certain rotational motions are there. The energies of that rotational motion are quantized. You can see that because you can measure these energies using spectroscopy. So let's do that. Last couple of minutes. I'm going to call this prefactor just B. Okay? And then I'm going to see what are the allowed values for the energy. Well, the first value is 0, so that's simple. The second value is when J equals 1. When J equals 2, and so forth, you can just add what the values are. And so what you see is that the allowed values for J equals 0, 1, 2, 3, 4, basically says these are the energy levels for rotational motion of this molecule. They're quantized. You see that? They are.